Good morning, cadets. Yesterday we have learnt about Biot-Savart law, right? Based on that Biot-Savart law, let us solve one problem, simple problem. The problem is like this: an element delta L vector is equal to delta x I cap is placed at the origin and carries a current 10 ampere. This is the element delta x which is placed along the positive x direction, and delta L vector is equal to delta x I cap. It means it is directed along the positive x axis. It carries a large current of 10 ampere. What is the magnetic field at the distance of 0.5 meter? What is the magnetic field at the distance of 0.5 meter along y axis, perpendicular to this? Perpendicular to x axis means about y axis. What is the magnetic field at this point? So, in order to solve this, the given thing is distance 0.5 centimeter and the length delta x, this length of this element is 1 centimeter, that is also given. So, we write first the Biot-Savart law. According to Biot-Savart law, magnetic field dB vector is equal to mu naught I dl cross r cap divided by 4 pi r square, where r cap is the unit vector and r is the distance. So, it is a cross product. So, r cap is along this, along y axis, that is about y axis means it is having unit vector j. So, it is having unit vector j. So, that is perpendicular to I cap, where I cap is the unit vector along x axis, right. So, if you write only magnitude if you write, then magnitude of dB equal to mu naught I dl upon 4 pi r square. So, this helps us to calculate the magnitude of magnetic field, and one can find out the direction of magnetic field using the right hand, as we have discussed in the previous video. If you point your thumb along the direction of current element, the current element here is ideal, and you see the current I is in this direction, which is 10 ampere. So, this is the current element ideal, that is delta L vector, right. The current is along the direction of x axis, ideal is along the direction of x axis. So, hold your thumb of right hand along the direction of current, along the current element, and you see the curling of the fingers. The fingers are pointing outwards, perpendicular to the plane of the board, and they are pointing outwards. Therefore, here is the dot. The dot shows the direction of magnetic field which is perpendicular to the plane containing both ideal and r vector, and the r vector is this, right, about y axis. So, perpendicular to the plane containing ideal and r vectors means, in this case, ideal is along x axis, ideal vector is along x axis, and r vector is along y axis. Obviously, the magnetic field should be about z axis. So, that is how we find out the magnetic field pointing perpendicular to the plane of the board. So, this is giving you dB perpendicular to xy plane. So, in this case it is xy plane. So, it is implying that it is about acting about z axis, from the diagram, from the convention. Now, let us substitute the values ideal cross r. Now, mu naught by 4 pi we know already, mu naught by 4 pi is 10 to the power minus 7, right. and r is given, r is 0.5 meter, and the delta x, you know, dl vector is equal to delta xi, this is given. So delta x is 1 centimeter. So 1 centimeter I cap. So 1 centimeter can be written as in terms of meter, 10 to the power of minus 2 meter. That is 0.01 meter I cap. 0.01 meter I cap. This is dl vector. Then current is also being given. Current I is equal to 10 ampere. Current I is equal to 10 ampere. And in this example, R cap represents J cap. R cap represents J cap because it is acting along y axis. So these things can be substituted in the equation. So therefore dB vector is equal to mu naught upon 4 pi. Mu naught upon 4 pi is 10 to the power of minus 7 Tesla meter per ampere, as we have discussed yesterday. So 10 to the power of minus 7 into current. Current is 10 ampere. DL is delta xi. Delta x, you see, it is 1 centimeter. So which is converted into 10 to the power of minus 2. So it is better to write 10 to the power of minus 2, so that it will be convenient to calculate in the powers of 10. 10 to the power of minus 2 I cap cross, and you see R cap. R cap is nothing but J cap. So that's how we get I cross J whole divided by 4 pi. Already it is substituted. R square. What is R here? R is 0.5. 0.5 whole square. So 0.5 whole square gives us 5 into 10 raised to minus 1 whole square. 5 into 10 raised to minus 1 whole square gives you 25 into 10 to the power of minus 2. 25 into 10 to the power of minus 2. That is nothing but 0.25. Square of 0.5 is 0.25. 0.25 can be written as 25 into 10 to the power of minus 2. So much of Tesla. So if you simplify this, you see 10 to the power of minus 7 minus 2. So I will write minus 7 minus 2 plus 1 and plus 2. When it comes to the numerator, it becomes plus 2 divided by 25, and here you see I cross J gives us I cross J, you can put it in the bracket. So I cross J gives us K, that gives us the direction of magnetic field about Z axis. So this can be further simplified as dB is therefore equal to 10 to the power of minus 9 plus 3. Minus 9 plus 3 becomes 10 to the power of minus 6. Minus 9 plus 3 becomes 10 to the power of minus 6 divided by 25. So this can be further simplified. So if you simplify this, the answer is about 4 into 10 to the power of minus 8. The answer is 4 into 10 to the power of minus 8 Tesla. So this is the magnetic field which is pointed about K cap. K cap. This implies magnetic field acts along Z axis, positive Z axis, which is pointing the plane of this board. So this is how we apply Biot-Savart law in order to solve the problem. Okay. Now we will apply Biot-Savart law. We use Biot-Savart law to find the magnetic field on the axis of a circular current loop. A circular ring, metallic ring carrying current. So that is what we call it as circular current loop. Let us consider that there is a circular current loop which is kept in this way. It is a circular loop. you see it is not kept. This is actually the loop carrying current, and this is kept vertical like this, so that it is kept in the xz plane, and this is the center, and this is x axis, and the loop plane of the loop, plane of the circular loop is perpendicular to this x axis, and assume that this x axis is the axis of this circular loop passing through its center, and this loop is carrying current. It is carrying current I, let us say, in this anticlockwise sense. Now we want to find out magnetic field due to this circular loop at certain point, let us say P, at this point P, which is at a distance r, which is at a distance x, from the center of this loop. We want to find out magnetic field at this point P, this is point P, which is at a distance x from this center of the loop, right? So for this we consider an element at the top, an element of length dl, and this is an element of length dl. Here it looks like this. If I choose this one as the center, and this is the center O, you can choose this center as O, right? So I am choosing one small element of length dl, and you see in this case when the current is in the anticlockwise sense, right? So here this becomes the direction of ideal vector in the anticlockwise direction, and at the bottom diametrically opposite, if you see exactly diametrically opposite, the element will be having the exact opposite direction of ideal vector, right? So this is the actual point. This is the actual picture which is kept vertical like this. So this gives us dl vector, right? So we will find out what is the magnetic field due to this ideal vector. Ideal vector, when the current passes through this small element, then it is called as current element ideal vector. So for this I should know what is the distance. This distance, if I draw, yes, this, let me call this one as r. Let us take this distance as, okay, small r, not capital R. Let us take this distance as small r, and the radius of this ring, let us take it as capital R. Capital R, radius of current loop. Loop means in this case it is a circular ring. R is the radius, I is the current flowing. Therefore, IDL is the current element which we are considering, so that I can apply the Biot-Savart law to this current element and get the value of magnetic field at this point P, right? So just I am going to write here the using Biot-Savart law. So I can write here using Biot-Savart law, I can find the magnetic field. So need not write it here because I have to draw the diagram here. So using Biot-Savart law, I can write dB, vector dB, you see vector dB equal to mu naught by 4 pi ideal cross R cap, ideal cross R cap divided by R square. Ideal cross R cap, you see R cap means it is along this direction, along the direction of this position vector R, right? With respect to current element, the R, small r, I will write that also. Here small r is the distance of P from ideal. So ideal cross R means it is along this particular point, right? So using this Bayes-Hurt law, I can now write dB vector is equal to, okay, dB vector is equal to mu naught by 4 pi into ideal by R square, ideal by R square, ideal by R square, because the angle between ideal vector and this distance vector is 90 degree. Look at this. When you look at the two-dimensional diagram, you will not feel it that the distance of this point P from this current element is making 90 degree with this current element ideal. It is subtending 90 degree with this current element ideal. So ideal cross R gives you definitely ideal into 1 into sin 90. Sin 90 is 1. Therefore, it becomes ideal. So if you want, I can write ideal into 1 into sin 90. So therefore, next it becomes, next step, mu naught upon 4 pi ideal divided by R square, because angle between ideal vector and R vector, R cap, you can write R cap is 90 degree. So to understand this, I can just show you, this is the circular link and this is the perpendicular distance, that is the axis. This is the axis of the ring, and here somewhere you are finding out, okay, okay, this is the axis of the ring, and somewhere you want to find out magnetic field at this particular point. So if you join from here to here, if you join this line from here to this particular point, you see on the axis, then this line that you are joining, definitely it makes 90 degree with this vector, 90 degree with this distance vector, right? That is what I have written, sin 90, okay, sin 90. You can take a bangle, you can take a bangle, circular bangle, and hold the pen at the center of the bangle, like this. Then if you draw a line from the end point to this point, or end point diametrically opposite from point to this point, it makes an angle 90 degree. Therefore, finally we get mu naught upon 4 pi into ideal upon R square. So that's fine. What about the direction? This is the magnitude. What about the direction? Direction, you see, ideal cross R. You are taking this ideal and cross R. You see the thumb. Ideal cross R. The thumb is, you see, sideway. Ideal cross R. It is like this. Ideal cross R. Ideal cross R. So magnetic field will be somewhat in this direction. So this becomes magnetic field dB vector, which is perpendicular to R vector as well as ideal vector. It is perpendicular to both R vector as well as ideal vector. So this becomes dB due to one small element. But I want to find out the magnetic field due to the entire circular ring. So I have to go on adding up such contributions of magnetic field due to all these current elements. This is one ideal, next ideal is here, next ideal is here, next ideal is here. So if you go on finding out, interestingly, you will get a cone of magnetic fields, which cannot be shown on the board. the magnetic field will be forming a cone due to all these elements. So, very interesting thing is, if you resolve this dB into its two components. One is component along y axis. So, this you can take it as dby, and another component you take it as dbx. You will find all dby perpendicular components are going to cancel. So, to show you how is it going to cancel, look at this diagram. Yes, I will just choose exact diametrically opposite element, which is here, exact diametrically opposite element, ideal, and from here if you draw, this becomes the distance vector r, and of course this is radius capital R. The angle is again 90 degree. So, exactly because of this ideal vector, you can see the magnetic field will be, again if you turn this ideal cross R, you see the thumb, ideal cross R, turn it towards R, the thumb is pointing outwards perpendicular to R vector. So, this becomes dB vector, you can call it as dB dash. So, again if you resolve this, this is exactly the dby dash, and here is going to be dbx. So, just I have taken one pair of diametrically opposite current elements. So, due to one pair of diametrically opposite current elements, due to the upper current element we get dB in this direction, magnetic field in this direction. Due to the lower current element, the magnetic field is in this shade direction. So, if you resolve this components of dbx is along x component, dby is along y component. Similarly, for this one, dbx is again along x axis in the same direction, dby you see exactly vertically downwards. So, for this one pair of diametrically opposite current elements, dby and dby being equal and opposite, so the y components cancel each other. In this way, we can say that for all these current elements, when you sum up the magnetic fields, when you sum up, all the y components cancel each other because they are exactly in equal and opposite directions of y axis. So, dby components cancel each other, and dbx components of all the current elements, dbx components add together. So, they contribute, finally magnetic field is contributed only along x axis. This is how we get it, right. Now, how to express this here? So, dB equal to this one, we got it, and this is as shown here. Let us say dB with angle theta with respect to dB with angle theta with respect to x axis. So, this I am taking it as angle theta, right. Now, if this is angle theta, very interestingly, you see this angle theta plus this interior angle is 90 degree. In the same way, this interior angle plus this angle is 90 degree, because dB vector is perpendicular to r vector. So, you can take this one as r vector, right. dB vector is perpendicular to r vector. Therefore, if this is angle theta, I can prove that this is also angle theta. I think you got it from the geometry. This theta angle plus interior common angle is 90 degree, because x axis and y axis are perpendicular to each other. In the same way, this interior angle and the common angle again when you add, it is giving you 90 degree, because dB vector is perpendicular to r vector. Therefore, if this is angle theta with x axis, then exactly r vector also makes angle theta with y axis. So, you can write here dB vector when resolved into dBy and dBx components along y axis and x axis respectively, all y components, dBy components due to the entire current loop cancel each other, and only dBx components add up, right, along x axis. So, now we will find out the total magnetic field, which is nothing but only x component, that is dBx. Okay. Therefore, magnetic field due to the circular current loop about a point on the axis is exactly along the axis, which is given by dB equal to dBx I cap, So, dBx, you know what is dBx? dBx is nothing but the x component of vector dB. Therefore, I can write entire magnetic field is equal to dBx I cap, because of adding up of all these magnetic components. What is dBx? dBx from the diagram, you can see it is nothing but dB cos theta. Now, we know what is dB. Already we got magnitude of dB as mu naught upon 4 pi I dl by r square. Already we got it. Then we will find out what is cos theta. Here we have got already dB equal to mu naught upon 4 pi I dl by r square, right. Then what is the value of cos theta? Cos theta can be formed from this trigonometry, from the geometry of this diagram. As I have said, if this is angle theta, we have proved that if theta is the angle subtended by magnetic field vector dB with x axis, then this theta is same as this angle. So, definitely if you draw this angle with respect to radius, the angle made by the distance vector with the radius, this angle is also theta, because these are alternative angles are equal. Therefore, alternative opposite angles are equal. If this is theta, then this is also equal to theta. Then I can very easily find out what is the value of cos theta. Cos theta is therefore equal to adjacent divided by hypotenuse. Adjacent is capital R and hypotenuse is small r. What is small r from the diagram? Using Pythagoras theorem, small r, you see this is x, small r is nothing but square root of x square plus r square. Therefore, I can write next step capital R divided by square root of x square plus r square, using Pythagoras theorem, right. Now, this I have to substitute here. So, therefore, dbx, finally db vector is equal to dbx is db cos theta. So I am writing what is db cos theta. Db cos theta is mu naught upon 4 pi into ideal by r square, into cos theta. So this is db into cos theta I am writing. Cos theta is r by square root of x square plus r square, into I cap. Yes, this is I cap. I cap means, as I have said, all the contributions of magnetic fields due to such current elements, when you sum up throughout the ring from top, when you go for one complete cycle and come back to the same, the magnetic field is found only along x axis, as I have proved. Y components getting cancelled each other. So further I can simplify now as mu naught upon 4 pi. You see, this r square is also x square plus r square. So I can write it as I r dl by x square plus r square whole raised to 3 by 2 I cap. So this becomes magnetic field. Right? Now the magnetic field due to entire circular loop, you have to integrate it. Now entire current loop b equal to vector b equal to integration of this db from, if you take this point as 0 and come back to this same point, it is going to be 0 to 2 pi r, 0 to 2 pi r. If you take this point as 0, when you take one complete cycle, the total length of this current loop becomes the circumference of this circular loop, which is 2 pi r. So 0 to 2 pi r. So here I can write same equation, taking out the constant mu naught upon 4 pi, and you can see x square plus r square, I r, these are also constant. So I r upon x square plus r square into integration of dl, only dl is variable, 0 to 2 pi r into I cap. So this integration of dl gives you the total length of the circumference, that is nothing but 2 pi r. Therefore I can write now total magnetic field. Therefore total magnetic field B vector is equal to Bxi. I got the Bx. Bx can be now written as integration of dl. Integration of dl from 0 to 2 pi r gives you total length of the circumference. Total length of the circumference is nothing but 2 pi r. So I can write it as where Bx is mu naught upon 4 pi I r upon x square plus r square, into 2 pi r into 2 pi r. Now 2 pi, 2 pi cancels here, you are left with mu naught upon 2. So here you are left with I r square. Therefore I am going to write here mu naught upon 2 into I r square whole divided by x square plus r square raised to 3 by 2 I cap. because it is along the x-axis. So, this is the magnetic field due to the entire current loop carrying current I. So, you can look at this. This is vector B equal to mu naught I r square divided by 2 into x square plus r square whole raised to 3 by 2 I cap acts. So, B is acting along the axis of the current loop. Right? This is it. Now, if you want to find out the magnetic field at the center, this is at a particular distance x, where r is the radius and this is small r as we have taken, and magnetic field is found out to be directly along the direction of x axis. So, this is dBx, so it is about x axis. That is how we got the direction of B along the x axis. This is important equation. It acts along the axis of the loop. So, this is direction of current which we have chosen, right, anti-clockwise. So, how to find out? Sign conventions. Using your right hand, curl the fingers along the direction of, curl your right hand 4 fingers, all 4 fingers along the direction of current, and see the thumb. The thumb gives you direction of magnetic field. The thumb gives you direction of magnetic field. Suppose I am drawing the circular loop in this way, in the anticlockwise sense, circular loop in this way. Then the magnetic field, you see, at the center will be along the axis, Is it upward or downward? That is the question. So, curl your fingers, all the 4 fingers of your right hand, and that gives you direction of current. That gives you direction of current along the anticlockwise sense. See the thumb. The thumb gives you direction of magnetic field. The thumb gives you direction of magnetic field. If you reverse the direction of current, suppose the current is along the clockwise sense, see the thumb points downwards. If the current is clockwise, the thumb points downwards, that gives you direction of magnetic field, right. This is how one can use the right hand rule, right, grip rule, right hand grip rule, right. Now, this is at a point x. If we want to find out magnetic field at the center, means this x is taken as 0. At the center, x becomes equal to 0. If you substitute x equal to 0 in this equation, the equation becomes very simple. Then V at the center, magnetic field at the center becomes mu naught I r square whole divided by 2 into x becomes 0, r square raised to 3 by 2, r square raised to 3 by 2, r square raised to 3 by 2, 2 cancels, so you are left with r cube. Therefore, this becomes mu naught I r square. You can see r square divided by r cube, I will write one more step, r square divided by 2r cube. So, you can cancel r square. So, you are left with finally B equal to mu naught I upon 2r. So, mu naught I upon 2r about x axis. So, at the center, therefore, we get magnetic field at the center. I will write the magnitude at center is now very simple equation, mu naught I upon 2r, where mu naught is the permeability of free space. I is the current and r is the radius of the circular loop. Larger the radius of the circular loop, lesser is the magnetic field. Smaller the radius of the circular loop, higher is the magnetic field strength, and B is directly proportional to the electric current, strength of the current. Higher the strength of the current, see, you can see B is directly proportional to I. So, this implies higher the strength of the current, larger the current flowing through the circular loop, more is the magnetic field, right. So, this is a very important discussion. So, in the next video, we will solve some numerical problems based on this. Thank you. Have a nice day. Bye.